Chapter 5, Stoichiometry. So this is the sort of chemistry that you may be familiar with from having done high school chemistry. This is also the sort of chemistry that people start to think of when they conceive of general chemistry as a subject. What we have done so far is we have talked about protons and neutrons and electrons and atoms, and we've seen how those electrons dictate the flavor and behavior of different elements. We've seen how those different elements have different charges and different electron configurations, and that dictates their bonding behavior. We took those elements, we bonded them together either covalently or ionically to make molecules. Now we're going to look at basically mass reactions in chemistry. So we're going to take this conservation of mass concept. We're looking at, I'm going to take some atoms in certain forms, so some compounds, I'm going to undergo a chemical reaction, and I'm going to recombine them into new substances. What do we do if we got some extra stuff, right? What do we do if we don't have enough stuff? How many grams of product can we form? And this is the sort of stuff that we'll talk about in this chapter on stoichiometry. So our basic rundown is 5.1. We'll talk about counting by weight. Then we will look at our atomic masses. And then we'll learn to solve some problems. We'll talk about the molar masses, percent composition of different compounds. Remember Dalton's original formulation about laws of definite proportion, right? And then determining the chemical compound of a formula. We'll look at chemical equations. We'll talk about balancing chemical equations. That's that multiple proportion stuff. We'll do some stoichiometric calculations, amounts of reactants and products, and we'll talk about the concept of the limiting reactant. So the preceding chapters have all been very conceptually based. There wasn't much computation for us to work with. There was wavelength to frequency, or we might have had a very basic conservation of mass, or maybe some really simple, here's an element, if I've got 10 grams of it, how many moles do I have? Now we're just going to really expand that. And to do that, we need to look at the mole. And the mole is really the central unit of chemistry, because once we've got things in moles, we can go in lots of different directions. So if we start off with moles of A, and we multiply by Avogadro's number, we can figure out the number of molecules we've got. If we know the molecular formula, we can figure out the number of atoms we've got of each kind. If we've got moles, we can figure out the mass using our molecular mass. If we've got a number of moles and we've got a concentration and molarity, moles per liter, we can go back and forth between a volume and a concentration to moles and vice versa. We will see in later chapters that we can substitute volume and pressure if we're dealing with gases. So the pressure of our gas, right, our pressure is going to be proportional to N. N is the number of moles. And our volume is going to be proportional to N, the number of moles. We can also go from moles of one thing to moles of another thing using our balanced chemical equation, and that process is called stoichiometry. So stoichiometry means counting, right? So it's basically like counting, or like finger counting. So we are counting the number of things that we've got. And this brings us to our central questions. Can atoms be counted? Does the number of atoms in a reaction affect the result? Can the mass of a sample be used to determine the number of moles it comprises? Okay. So let's talk about our average mass. The average mass is used to determine the number of atoms in a set quantity of a substance. It's determined using a sample of the substance, so we get the average mass, and we'll take the total mass divided by the number of the atoms. Atoms do not need to be identical in order to be counted by weighing. And this led to our system of atomic masses, and our modern system of determining atomic masses was first used in 1961. Right, so it's not that long ago in terms of the history of chemistry, right? You will probably have some professors on campus who were well around and alive during the 1960s. It's based on carbon-12. So it's kind of a definitional sort of thing that says, all right, we're going to take carbon-12 and we're going to say that 12 atomic mass units, if we've got carbon-12, carbon-12 is 12 atomic mass units, and everything is going to be based relative to this carbon-12. The most accurate method currently used to compare masses of atoms involves the use of a mass spectrometer, and that's a machine in which atoms are passed into a stream of high speed of electrons that convert them into positive ions, cations, positive, Meow. These ions are then passed through a magnetic field and usually an electric field if we're going to be doing this kind of high resolution mass spectrometry, accelerating the ions, create their own magnetic field, resulting in a change in the path traveled. Basically, what you're doing is you are sending these guys down a chute, and if you have a magnetic field and an electric field, just like we saw with Thomson's experiments, you've got a charged particle moving through, it's going to be deflected. The degree of deviation or deflection depends on the mass of the ratio. Really, it is the mass to charge ratio. Ions with higher masses deviate the least, right? So you can imagine one that's got 2 charges on it, it's going to, and if it's got 2 charges but twice the mass, it'll end up at the same point. Deviated ions hit the detector plate, and comparing the deflected position of each ion gives us their mass. So this is one of these really simple mass spectrometers. Our sample comes in here, pew, 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 right? We're going to turn it into ions. This ion beam gets accelerated, zoop. It goes to this magnetic field. This magnetic field is going to deflect it. And so you think of it as like having a magnetic push that's going to deflect the particles. If you're a light particle, that push bends you more. If you're a big, heavy particle, it bends you less. And so our most massive ions are going to be deflected the least, and our less massive ions are going to be deflected the most. And you can scale what happens at this output, so this detector plate. Back in the olden days, they just used like a photographic film, and they might have put like a scintillating plate in front of it, like Rutherford did with some zinc sulfide on it or something. This is a very simple mass spectrometer. Mass spectrometry is one of the premier analytical chemical techniques. We could do an entire class on different types of mass spectrometry. It is certainly very powerful. If you look at any of the crime shows, one of the things they're going to do is they're going to say, let's run it through the GCMS, right? Well, the GCMS stands for gas chromatography mass spectrometry. So mass spectrometry is a very good technique at identifying things, not just determining how heavy atoms are. So if we look at our C12 and C13 in a mass spectrometer, we get the ratio of these two masses, the mass of C13 over the mass of C12, and we end up with 1.08 and a whole bunch of extra decimal places. Based on the definition of the atomic mass unit, the mass of carbon-12 is going to be, right, 12 atomic mass units, our definitional amount from carbon-12, times this 1.083612 that we got out of the instrument. So it's 13.003355 atomic mass units. The average mass for an element is also referred to the average atomic mass, or the atomic mass. So what you see on that periodic table, and even though carbon-12 has 6 protons and 6 neutrons, carbon-13 has 6 protons and 7 neutrons, it's going to end up looking on the periodic table like you got an atomic mass for carbon a little bit above 12, and that's because you have naturally occurring carbon-13 atoms out here on Earth. Now, if we went to Mars, or we took our mass spectrometer out into space, and we did some experiments out there, we could end up with a different natural abundance. That's our ratio of each of these two isotopes for any one of our elements. So when we look at our periodic table, it's not a nice even number on that atomic mass. And that's because we've got different isotopes. Those isotopes are in different ratios. Those ratios are specific to the planet Earth, right? Because that's where we're doing all of our experiments. If you get to be a astronaut and you work on the space station or on the moon or on the Mars, you hold up a little sign that says, I took chem with Dr. Stewart, and thank you for teaching me about atomic masses, because I will want to horn in on your fame for that, because that would be awesome. So hopefully one of you will do that. So let's look at the average mass of an element. When a sample of natural copper is vaporized and injected into a mass spectrometer, the results that we'll see in the figure are shown. Use these data to compute the average mass for natural copper. So the mass values for copper-63 and copper-65 are 62.93 atomic mass units and 64.93 units, respectively. So the information we need to calculate the average mass of natural copper, we need the mass of each of our isotopes, which we've got that, and that's our information available. Then we're going to determine the mass of 100 atoms of natural copper. Right? Why 100? Because we're talking about percent, right? Pick a number that's going to make your life easier. Go with 100 atoms. as shown on the graph, every 100 atoms of natural copper, 96.09 are going to be copper 63, and 30.91 are going to be copper 65. So all we've got to do is we're basically going to do a weighted average for those. So in that 100 grams of copper, we're going to start off with 96.09 atoms, and we'll multiply that by 62.93 units per atom. And then we're going to add in our 30.91 atoms of our other isotope of copper, and it's going to be at 64.93 atomic mass units per atom, giving us a total of 6,355 units. So our average mass of copper, we're going to divide that by the 100 atoms we took it over, and we'll get 63.55 atomic mass units per atom. Okay? So look at conceptual problem solving. It's a flexible and creative method for solving problems based on the fundamentals of chemistry. An understanding of the process is used to determine the answer to problems, which is going to be essential for us going forward. Right? We've got two ways to approach a problem. Neither is ideal. One is pigeonholing. Like sometimes you can get really focused on narrowing down and defining the parameters. Another is the big picture. So what does this mean in the grand scheme of things? How is this working out in the universe? Right? Both are going to have their own inherent limitations and advantages. So do you go big? Do you go small? Do you do a bit of both? Right? So let's look at some of our problems. So steps to solving a problem. Where are we going? Right? So what is our final goal? Right? Oftentimes in a Gen Chem class, if I'm asking you a question, that's going to be the who, what, where, when, how much, how many. We're going to look for our question words. Where do we stop our analysis? Where do we stop our questioning? How do we get there? What path are we going to take? Right? So given the stuff we're starting with, how do I get to this goal? If I want to walk from here to Montana, what resources do I have? What route am I going to take? Would it make sense to fly? Should I drive? We got lots of things to consider on how to get there, right? Based on what we're given. So, and then at the end, you want to do a reality check or the is it plugged in check, right? So if anybody has ever worked in IT or customer service or any of those jobs where you have a people-facing job, right? You sometimes need to do that like really basic, does this make sense kind of check at the end, right? My computer's not turning on. Did you plug it in? Oh, yeah. And myself has done that, right? I've gone through like, man, there's nothing working, man. I can't figure out what's going on. Oh, I didn't plug it in, right? So, make sure that your answer makes sense, right? When you do that, like orders of magnitude are great clues. Like if you've got like 3 grams of something over here and 4 grams of something over here, and your answer ends up as 2,000 tons of stuff, maybe something went wrong. Another good clue for that is look at the units, right? If you were expecting a unit of joules per mole at the end, and you end up with liters times grams, right? Something went wrong, right? So use those things to double check yourself, right? Do the reality.